Part B, the title, variable size reduction. Yeah. In part A, when we do divide and conquer, what kind of reduction we did in part A? Size 1 reduction. Every time we reduce the problem size by 1. Yeah. So that's a very commonly used reduction way. In this part, we will do two other different types of problem size reduction. The first one, B.1, reduce problem size by half, cutting half. Yeah. So let's look at the question. Yeah. Problem 8. Count binary digits. Yeah. Oh, yeah. All right. Let's look at the problem. Given a positive decimal integer n, find the number of binary digits, bits, right? The number of bits in its binary representation. Yeah. It's a simple question. Yeah. But we want to use this question to study recursion. The recursion, we do divide and conquer. Yeah. When we do divide and conquer, we do it in a different way. Yeah. All right. Now, first, let us review the binary representation. Yeah. That's the main formula we need to use in this question. Let's recall, in our discrete math, we learned this binary representation. How do we represent this integer n in the binary representation? Yeah. Let's recall the formula. Okay. This is the formula. Yeah. And left-hand side, we use the decimal system, decimal numeral system. Yeah. When we use the decimal system, we use the number base. Base is 10. Okay? Yeah. Now we switch to the binary numeral system because computer internal calculation uses the binary numeral system. Yeah. But when we switch to the binary system, we change the base. Yeah. The value, we do not change the value, but we change the base of its representation. So here you see we use the base in this way. Okay? All right. Similarly, so here the general representation, if you change to a different base system, you can do things similarly. Yeah. Here, let me show you another system called ternary system. Base 3, ternary system. Okay? If we change to ternary system, B0 plus B1 times base 3 to the first, base 3 squared, and so on. Okay? Yeah. Yeah. So the structure is like this. Yeah. Because in our decimal system, we just change the base to 10, right? So that's the decimal system. Yeah. So very general. In this way, we have a general representation for, let's say, canary system. How about that? Base K. So canary system. Yeah. We can use this way to represent. Yeah. All right. Now, let's work on this binary system. Yeah. All right. Now you need to do observation on this representation. Any special property you can observe to be used in our formula transformation. Remember? Yeah, in problem solving, yeah, when we need to work on our problem, we need to do formula transformation. But when we do formula transformation, you need to do a very good observation. Try to discover some hidden property. Here, what kind of property? You can, observe. Interesting property. Interesting property. Base 2. Look at the base 2. Anything special the base 2 can give you, you can, extract from that base 2 representation. All right, yeah. So we need to take advantage of the structure for base 2. How do we think about? If we do division by 2, both sides, what would happen? Yeah. Division by 2, both sides, what would happen?
That means the exponents would all go down by 1.
Yeah, go down by 1, but still power of 2, right? Yeah.
Still like coming to the power of 2.
Right. Yeah. Yeah. But there is a fractional part, right? Possible fractional part. Yeah. But in our computer science, when we do division by 2 for integers, we frequently do integer division, right? Yeah. Yeah, because we like integers. Okay. In computer science, we like to work on integers. Yeah. Now, let's do integer division. Okay? Let's do integer division by 2. Yeah. All right. So then, yeah. All right. Yeah. So here the condition. Yeah. So we can assume the most significant, this B sub S, we call the most significant bit. We can assume non-zero. Yeah. Otherwise, we just go to look at the next one. Yeah. 0, so we, eliminate it. Yeah. All right. Then, yeah. Here we can see, because the goal, find the number of bits. Here, each B coefficient corresponds to 1 bit, right? Yeah. Each B coefficient corresponds to 1 bit. So we only need to count the number of B coefficients. B coefficient. When we count, can you see why the answer is S plus 1? Can you see that? So here, let's recall a method we used several times before. How do you count the number of bits here? Any special method we can use? Counting by reference. Counting by reference. So when we do the counting, let's find appropriate reference. Each B coefficient we can associate. We can do 1-to-1 mapping with the subscript. 0, 1, 2, and so on, S. So then, let's look at the objects, subscript objects, to be mapped by all these coefficients. Let's list all the subscripts, starting from 0, 1, 2, consecutive integers, the last one, S. Now, can you count how many integers in this set? Consecutive integers, S plus 1, right? Because you have 0. Okay? If you ignore 0, you have S, right? If you cover that 0, you have S. But now you need to include that 0. So you have S plus 1. All right? Yeah. So here we have the answer S plus 1. Yeah. The question, is this the final answer? Is this the final answer? S plus 1. Can we say, we find the answer is S plus 1. No. It's not the final answer. Okay? Why? The question, what is S? What is S? Right? Yeah. So we know S comes from that most significant bit. Most significant bit. Yeah. But yeah, look at the given question. The given question, our input number is only one number n. That's our input. Okay? Yeah. If we plug in our input parameter, that's only one parameter n. Then we need the output. So our function should generate some output, but the output must be in terms of the input number. Yeah. This S is not the input number, right? Yeah. So it's some, intermediate variable. S is an intermediate variable. Yeah. So we should write S in terms of n. Yeah. So our function should be applied on the input number n, not some uncertain intermediate variable, right? Yeah. Yeah. So we need to do more work. Yeah. All right. So then, our current goal, we need to find the representation for S in terms of n. Then we're done. Okay. All right. Next. Yeah. All right. So we decide we do division by 2, integer division. Now let's look at the division result. Division result. Yeah. So left-hand side, we need to use the floor function. Yeah. Right-hand side, you can see, right-hand side, nice representation. Okay? Yeah. So binary representation, yeah, but, similar structure as the original structure. Yeah. All right. Based on this new representation, what conclusion you can get based on this structure, new formula? Yeah. Now, we need to make a conclusion. Yeah. After we derive this formula, we need to make our conclusion. Okay? Yeah. So what's the conclusion? Yeah. All right. Because for this question, you can see we have two representations. The first one is the original representation. The second one, a new representation. Okay? Yeah. Then, another concept, problem size. What is the problem size of this question? Remember, we used this concept many times before. Problem size. Yeah. Here, problem size. Okay, this is problem size. Yeah. Here you can see the way we use the concept problem size here is different from what we used before. When we use the concept problem size before, we mean number of elements in an array, right? That's our problem size. Number of elements. Counting number. Yeah, number of elements in the given array. That's the problem size. Yeah. Here, it's not a counting number, right? Yeah. So this is a different way to use the problem size. And the problem size here, it's another counting number. We call it magnitude. Yeah. Another case for the problem understanding for the problem size, magnitude. Magnitude. Okay? Yeah. Yeah. So one number, but how large is this number? Okay? So that magnitude, we treat it as the problem size. Because the larger this number, the harder, right? Yeah. So matches our general understanding. Yeah. All right. So here you can see these two formulas related to the binary representation for two different problem sizes. Two different problem sizes. Okay? So the same binary representation problem, but in two different problem sizes. That's our understanding. Okay. All right. Then, our next question. What's the relationship between these two questions of different problem sizes? Relationship. Yeah. Yeah. If we can find that relationship, then we get recurrence relation. Yeah. We want to find the recurrence relation between these two problem sizes. That's our goal. Okay? That's our current goal. Yeah. All right. Yeah. So next step, we need to, look at the recurrence relation. Yeah. Oh, yeah. All right. Yeah, so here you can see observation. The first one, yeah. So what is the change? Yeah. Here, we want to consider the change, right? Changes. Okay? All right. The first change, the least significant bit is removed. B0, that's the least. When we change from first representation to second one, we cross out B0. Yeah. That's the first change. Okay, all right. The second change, yeah. Now let's do the counting on the number of bits in the second representation. We can see the answer is reduced by 1. Yeah. Yeah. Answer reduced by 1. All right. Yeah. Okay. Yeah. So this observation can give us the recurrence relation. Yeah. The difference between these two representations, it's 1, the difference. Okay? Yeah. Yeah. So now we are ready to write the recurrence relation. Okay? All right? Yeah. Yeah, the problems, yeah. And another property, the problem size, yeah, because you look at the problem size reduction. The size reduction by half, by approximately half, yeah, we can call half, okay? Yeah. Yeah. Good approximation, very close to half. Yeah. So we are very satisfied with this approximation, so we just call it reduce. Problem size is reduced by half. Yeah. All right. Now, recurrence relation. But we need a function, okay? Yeah. In order to write out recurrence relation, we need an explicit function for the representation, right? Yeah, yeah. So the function, we give a name. Being binary recursion, right? Yeah, there's a name, binary recursion function being rec of n, problem size n, okay? So this function should give us the number of bits for decimal number n, okay? Positive decimal number n, yeah? So that's the meaning. That's how we define this function. Based on this definition, yeah, so the number of bits left-hand side, yeah, equals, yeah, So we use the second representation. Yeah. The number of bits of the floor function of n over 2, we know the difference is 1, so we plus 1. We get back to the original number. That's the recurrence relation. Okay? Yeah. We know that when we apply the recursive algorithms, the main step, the key step is the recurrence relation. That's the key step. After you derive the recurrence relation, almost done, right? Yeah, because we know how to write a program, calculate this binary recursive function, right? Yeah, very easy to write the implementation code. Yeah. But how to derive it? That's not easy, right? Yeah. So we need to do a lot of analysis. Okay, apply our problem-solving skills to find this recurrence relation. Yeah. All right. Yeah. All right. But now, next step. Yeah. Next step. We want to find a solution. Find the solution. Yeah. All right. We need a base case, right? Yeah, we need a base case. If n equals 1, then 1 bit. Yeah. So that's the base case. Okay. All right. Now, let's solve this recurrence relation. Yeah. To solve it, yeah, so here. Yeah. Yeah. Why we solve it? Why we solve it? Yeah, so here. Because if this recurrence relation is known, we can write an implementation code easily. When we write an implementation code, we don't need to find explicit solution of this function, right? Yep. We don't need to write explicit solution. We just, compile, execute our code. Yeah. So that's the computer science way. Yeah. But another way, yeah, if this problem can be solved mathematically, yeah, yeah, then we can find a final formula for the recursive function. If the final formula is not too bad, if the final function is a good function, then we hope we find a clean, nice final formula. Then we do not need to write the program. We just plug in input number n into our formula. Then the formula will give us the answer. That would be faster than you execute your program, right? Yeah. Because execute program, so you have a loop, right? Recursion. Yeah. Remember? Yeah. Loop recursion. Okay. You need to spend some time to do the calculations. So here the formula, plug in formula internally, although the formula also needs to be implemented. Yeah. But that formula implementation in general will be faster than the program implementation. Okay? Yeah. So if we have a formula, we prefer using the formula way to calculate the answer. If we do not have the formula, then we have to take the programming way. Yeah. All right. So now let's try to get a formula. Yeah. All right. And here, another thing, yeah. Inside computer, when we do integer division, but it's not an arbitrary integer. The divisor, here the divisor is not a random integer number. It is the most desirable number we like to use, 2. Base 2, binary. So it's the base of the binary system. Base 2, that's nice, right? Yeah. So when you do division by 2, let's think about inside CPU, how to do the division by 2. Inside CPU. So here we need to get into the CPU. Internally, how to do the division by 2. Yeah. So here, let me give you some simple background. Yeah. Let you appreciate the importance of the division by 2. Yeah. All right. Let's recall. Do you remember in our module 1, we compare addition and multiplication, right? Yeah. Do you still have some impression how much is the difference? The execution time used for one addition, one integer addition. Here, let's talk about integer addition. Okay, one integer addition and one integer multiplication. What's the ratio? Do you still remember? What's the ratio? In our assumption, 10, right? 1 to 10, right? 1 to 10 ratio. Yeah. If we use 1 nanosecond to calculate one addition, then if you calculate one multiplication, you need 10 nanoseconds. 1 to 10 ratio. Okay, all right. Now let me give you another relative number. If we want to do integer division, do you know how slow? Integer division in CPU, inside CPU. Okay, yeah. So, wiring, very complicated. Yeah. Let me write it out clearly. Okay, all right. Yeah. Addition over multiplication colon division. Okay, all right. So here, I talk about integer. Because for the floating point, these things even slower. Integer, relatively faster than floating point calculation, equals approximately. Here we can, definitely approximately 1 to 10 to 40. That's slow. 40 division. Okay? Much slower. Okay? Yeah? Yeah. So if you do general integer division 40 times comparing with addition. Yeah. If you compare with multiplication 4 times. Okay? 4 times. That's much slower, right? Fortunately, yeah, that's why I like to, give you the evidence for the appreciation. Fortunately, here, the divisor equals 2. That's just the base number of our binary system. Base number. Okay? Where we do division on the base number or power of the base number, then we do not really need to do the usual integer division. We just move the binary point, right? Shift. That's why here, when you do special division on the base number or power of the base number, basically you just do the left shift operation. You move shift operation extremely fast in CPU because you do not need to do calculation. Move shift, you are done. Okay? Shift the binary point, complete. Extremely fast. And this left shift operation even faster than addition. Faster than addition. You see? Yeah. If you do the regular division, you need 40 times of the addition. But if you just move the binary point, you will do faster than addition. How big is the improvement, right? How big is it? Yeah. So we prefer to do the shift operation, if possible. Yeah. Yeah. All right. If possible, yeah, we like to use shift operation. Division by power of 2, we just do shift operation. Okay. Yeah. Multiplication power of 2, we do shift operation, right? Yeah. Multiplication, we do the shift to the right. Division, shift to the left. Extremely fast. Okay, all right, yeah. Now, let's go to the next step. Now our goal, we want to find the formula. All right, all right, all right. Yeah, and here, all right. So now. We define another function, a of n, as the number of additions. Yeah, because here, this is our base operation. Yeah, we do addition, add 1, base operation. Okay, now we want to count the number of our basic operation. Yeah, yeah. So a of n. Yeah, then we can easily, from the original recurrence, we can easily see the recurrence relation for this a function. Yeah. We have a similar recurrence relation here. Okay? Yeah. Yeah. All right. Yeah. So then, yeah. So we can work on the simpler, although this equivalent. Yeah. All right. But when we work on this one, here I do some analysis. Yeah. Yeah. How to calculate, how to find the solution, how to find the solution of this recurrence relation. All right. All right. But here, in our problem solving, we can see the hardest part in this representation is the floor function. Is the floor function. How to control, right? Yeah. So there is some uncertainty here. Yeah. Because n over 2, sometimes you need to round it down, right? Sometimes you do not need to round it. Yeah. Sometimes you take the same value, sometimes you need to round it down. So there is some uncertainty here. Okay, all right. So in problem solving, how to control the uncertainty? That's a main issue. Some main issue here. Yeah. All right. So in this situation, how to handle that floor function? Do you want to simplify it? Yeah, because the floor function brings us some technical difficulty. We want to remove this technical difficulty. So what's your plan to remove the technical difficulty? Okay? Yeah. All right. Yeah. All right. The floor function, when n is an even number, we do no change. Okay, but n is an odd number. Then we need to change a little bit. Okay, n minus 1 divided by 2. Yeah. All right. So it tells us there are 2 cases we need to work on. There are 2 cases. Right. In this situation, there are 2 cases to work based on what we learned before. When there are 2 cases, what should we do? When there are 2 cases, what is our typical strategy to do? typical strategy. Yeah, which one is easier? We want to work on the easier case, right? Yeah. Even case easier or odd case easier? Even. Yeah, even case easier, right? Yeah. So in this area, let's work on the even case first. All right, simpler, so let's work on the even case. Yeah. Another question. Because when we work the first round, yeah, we need to work several rounds, right? The first round, can we make our problem the simplest possible situation? Yeah, because it's the first round, okay? First round, we want to simplify our given problem to the simplest we can get. The simplest we can get, all right? Yeah. Then, wish to have. Huh? So we can make our wish because that's our first case. We can make some wish, okay? Yeah. Make assumptions. So wish here, you can make assumptions, okay? Yeah. Yeah. So this assumption should provide us the best scenario. The best scenario. Imagine that. So what's the best scenario here? Because the best scenario should target the floor function representation. Floor function representation. So in your best scenario, all the floor function gone. All the floor function representation all gone. Then that's the best, really the best. All gone. Okay? So what is that best scenario? Okay? All right. So let's look at in order to see that, the best case scenario. The first time when we want to remove the floor function. So our assumption should be we wish n even. Yeah. All right. But the second time, yeah, because we need to do recursion many, many times, right? So our second time, the left-hand side floor function give us, no rounding number, right? Yeah, no rounding. Yeah, but right-hand side, n/2 floor function, then there is a possible rounding, right? Possible rounding, yeah, at the right-hand side. That's, we want to eliminate it, okay? So you can make more assumption, all right? You can make more assumption. So that this assumption, we wish n/2 to be even. How about that? When n/2 is even, then no rounding at the right-hand side floor function representation, right? Yeah, we can make our wishes because we want to consider the best case scenario, all right? Yeah. So if people ask you why can you make so many assumptions? Because you just answer because we want to consider the best case scenario in our first round problem solving. Okay? Yeah. So make sense? No problem? No. All right. Then, because we need to do the recursion like this all the way down to the bottom, and we want to make sure no rounding for all the floor function representations, right? That's the best case scenario. So at the end, you can see, in order to get that best case scenario, we need to assume n is the power of 2. Then, all rounding are gone. Okay? Yeah. All the rounding cases all gone. That's the best case scenario. Okay? Yeah. So that's our first assumption. After this analysis, now we can make our assumption. All right. Our assumption this time, we let n equals 2 to the k, power of 2. Power of 2. Okay, all right? Yeah. Now, if we want to use k number, that is log base 2 of n. Based on the definition of logarithm, k equals log base 2 of n. Okay, all right? Now, new recurrence relation. This time, let's simplify our original recurrence relation, new recurrence relation. Now you can see floor function is gone. Yeah. Floor function is gone. Okay? Division by 2, because it's an integer, right? Every time when we do division by 2, we get an integer. So the floor function can be removed without any change. Yeah. That's why we call it the best case scenario, right? Yeah. All right? Yeah. Yeah. And also we have base case. Yeah. So base case. Now the question, how to solve this new recurrence relation? New recurrence relation. Okay? All right. All right. All right. So let's do the work. All right. All right. So first recurrence relation, second recurrence. So let's list all of them. Okay? One by one, all of them, from beginning to end. Okay? From beginning to end. All right? Then, yeah, dot, 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 yeah, ellipsis in the middle. In the middle, yeah. Then another question. How do we keep track of all these equations? Yeah. We have a question. We need to, yeah, because in the middle, we skip unknown number of equations, right? Yeah. We cannot list all of them, okay? Yeah. Impossible. Technically impossible. So we skip uncertain number of equations in the middle. Yeah. How do we keep track of all the equations? Any idea? We learned before, some method we used before. Keep track of our data in this situation. In this situation. We want to keep track of the data. How to keep track of? So I give you one special method before. There is a special property we can use to keep track of the data. What's that? In our first chessboard, can you connect to the chessboard question? Yeah? Invariant. Invariant. Yeah, invariant. Yeah. All right. So, but here we need to know the invariant. All right? Yeah. Yeah. What's that? Look at the exponent number, k minus 1 exponent number, okay? And, sorry, yeah. This invariant, yeah, actually, sorry. Yeah, here, actually, yeah. Here, that, because this here, the situation is simpler than our, invariant situation. Simpler, yeah. Here, we do not need to use the invariant. Here, when we do the counting, so here we need to do the counting. Because here, we only need to count the number of equations, right? When we do the counting, we have another method, easier, convenient method than the invariant method, counting by reference. How about that? Counting by reference. Yeah, we don't need the invariant, okay? So the invariant, we treat that advanced method. Here, we use the simple way, counting by reference, okay? Yeah. Reference, what reference do we use? Yeah, you have many different reference objects you can choose. Okay, all right. You can choose exponent at the left-hand side, okay? All these exponents at the left-hand side, okay? So you have a list of reference objects. 1, 2, 3, K. Okay? Reference object. How many? Easy, right? Yeah? K. K equations. K equations. So you have K equations. Okay? All right. All right. But when you add up all these equations, you can do cancellation, right? Yeah. Left-hand side term, right-hand side, same term, you can do cancellation like this. Okay? You can do a lot of cancellations like this. Okay? Yeah. All right. So then at the end, a of 2 to the k equals k. Why k? Because there are k equations. Okay? There are k equations. And this one, that's the base case. Yeah. K equations, so you accumulate k1s, right? Yeah. You accumulate k1s from k equations. That's this k. Then, what is this last one? Comes from the base number. Base number, okay? So you get an answer. You get an answer. K plus 1 in terms, yeah. So here, in terms of the intermediate variable, k is an intermediate variable, okay? Yeah. Yeah. It's not an n, yeah. It's not an n, yeah. All right. So we find the answer, but it's not our final answer. This is our current answer, but it's not the final answer. So we need another step to get our final answer. Our final answer should be in terms of n, not k. Can we do that conversion easily? From k to n easily? Yeah. All right. Let's do it. All right. Yeah. 2 to the k, based on our assumption, 2 to the k, that's n, right? That's easy conversion. Replace 2 to the k by n. Then k, we know that's log base 2 of n. Yeah? So if we write it in terms of n, we have this representation. Okay? This formula supposed to be our final answer. But do you see any problem here? Yeah. This one is supposed to be our final answer, but is there any problem? For it to be used as our final answer? Look at the log base 2 of n. Log base 2 of n. Okay, all right. So here the problem is this representation. Think about it. This representation only makes sense for n is power of 2, right? If n is not a power of 2, it does not make sense, right? Yeah. Because if n is not power of 2, the right-hand side must be an integer because we count the number of additions. Number of additions must be an integer. But log base 2 of n won't be an integer, right? Won't be an integer. Yeah. So for the general case, the right-hand side expression won't be an integer expression. So it won't be the exact formula we hope to find. Yeah. So what shall we do next? What shall we do next? Yeah. Okay. Yeah. We need to fix it. Fix the problem. Because left-hand side, right-hand, not compatible. Yeah. Integer, non-integer. So integer expression, non-integer expression, not compatible. So in this situation, how do you make them compatible? The both sides must be compatible. Okay? Yeah, all right. Yeah. All right. Now, when we move to the general case, we need to make some change to make the expressions compatible, both sides. Yeah. All right. So for the general case, we need to make our guess. Here, guessing. Guessing is important. We need to make our guess here. Okay? All right? Yeah. Yeah. So in scientific research, guessing is extremely important. How people discover new scientific results. Most of the time, people use guessing. Okay? Yeah. Guess and verify. You guess, but you do not know if it is correct. You need to do a lot of experiments to verify it. Okay? So when you do this, yeah. So if you verify it's correct, you make progress. Okay? So that's the scientific research. Yeah. Scientists, yeah, most of the time they do research in this way. Guessing is so important. Here we need to make our guess. Okay? Make our guess. All right. Now, for a general integer not power of 2, a of n, yeah. But when we make our guess, look at the base of our guess. This is the base of our guess. We have a solid base. Okay? Yeah. So it's not a guessing from air, right? Yeah. So you have nothing. You make a guess, but you have nothing. You start from nothing to make a guess. Is that hard? That's hard. Blind. You make a blind guess. That's hard. But now we have a solid base as our starting point. This is our solid base as our starting point to make a guess. That's not hard, right? Yeah. So when we make the guess, so our idea for this guess is the number to be guessed should be close to this one, right? Not far away. Okay? Yeah, because this one, when n is power of 2, exactly this one. But it's not power of 2, near this number, right? So that's our understanding. So the guessing number should be close to this one, but also it should be an integer expression. That's our guidelines for our guess. So based on this, what kind of guess do you want to make? Based on these two guidelines, what kind of guess do you want to make? Hmm? Two guidelines. Yeah, two guidelines. The first one close to this expression, first guideline. Second, must be integer. Must be integer. Okay? Yeah. Use floor function, ceiling function. Floor function, ceiling function. Yeah? Satisfy both guidelines, right? Because when you use floor function, ceiling function, they are integers. Are they close to the formula? Yeah. You change a little bit, right? Floor function rounded it down. Ceiling function rounded up, right? Close to this one, yeah? Follow those two guidelines. Okay? Good. Yeah? Yeah. So let's write it out. First, sorry. Yeah. Yeah, messy. Yeah. Let me, all right? So we have two possible guesses. The second one is ceiling function. Okay? But which one should we pick? Yeah, because these two still some uncertainty there. So we want to make it more certain. Yeah, so in these two possible guesses, we want to pick a better one. There is one. One should be better than the other, right? Yeah. So which version you feel it is better? In this situation, what should we do? Not guess, experiments. Remember, guess and verify, right? Later, I will talk about another strategy, guess and verify. Guess is our first step, but second step, you need to verify it, right? You need to do the verification to, to see how good is your guess, right? So you need to do the verification. So now we need to do the verification step. Oh, sorry. Yeah. The verification step, let's try when n equals 3 for verification. N equals 3 when we write the binary representation. You know the binary representation, right? Of 3. Yeah. Equals 1, 1 base 2. Okay? Yeah. Parenthesis 1, 1. Right? Yeah? Binary representation for 3. 1, 1. How many bits? 2 bits, right? So that means if you plug in n equals 3, your answer should be 2. Okay? 2. All right. So let's take a look. In these two formulas, when we plug in here, the bottom version, 1 plus seeding function log base 2 of 3, seeding rounded up. 3 is greater than 2. So 1 point something, right? Rounded up, it's 2. 1 plus 2, this equals 3. And here, this version, 1 plus floor function log base 2 of 3, rounded it down. 1 point something, rounded it down. That's 1. 1 plus 1 is 2. Based on the verification, because here our experiment tells us 2 should be the right answer, right? Not 3. Okay? That's now it tells us we should use the floor function version, not the seeding function version. Okay? Yeah. So that's the problem solving. Look at C. Yeah. In our whole process, you can see how much knowledge we should have to get us this far, okay? To get us this far. Close to the destination. Right now, very close to the, but it's still not there yet, right? Still not there yet. Okay? Yeah. At this point, still, you have one more step left to your destination. What's that? All right, so now this formula is our best guess. Can we say that? That is our best guess. But how do you know your best guess is the correct answer? You don't know, right? Yeah. You only know you have your best guess. But you didn't prove it. So the last step, you need to prove it. You have the best guess, but you need to rigorously prove it's correct. Rigorously prove it correct. It's correct. So this last step, how to prove it in this. So you have a solid guess. Now, here, we're very satisfied with our guess. Very solid. Okay? So now our goal, we want to using some special mathematical tool to verify this formula. That's what we want to do. Now, we need some help. Help from a powerful mathematical tool to help us prove it.
Power of math tells you.
The power what?
The power of math tells you.
Yes. Yeah. Power of, so here, that powerful tool, mathematical induction. Let me give you that power. Okay? Yes.
the base case.
Yes.
And then,
Strong, right?
and
Yeah.
then the inductive hypothesis.
Yes. Yeah, yeah. Exactly that. So here, mathematical induction. All right? Yeah. Yeah. But here I would like to skip the step. Okay? Yeah. I would like to skip the step to save some time. Save our precious time. Yeah. But later I will show you mathematical induction only once. Later we have another formula we need to apply mathematical induction, but I just show you once. Yeah. I do not show you mathematical induction twice, here and there. So here I skip. So there, still in our module 3, at the end of our module 3, so then I show you mathematical induction. Okay? All right? Yeah. So we complete this topic. Next topic. Yeah. I do not have much time. Next topic. Just give you some introduction, short introduction. One slide. Let me do one slide so we will finish today. B.2, variable size reduction. Problem 9, greatest common divisor. Calculate greatest common divisor. Yeah. First, you know the definition, right? Yeah. So the problem, given two non-negative integers m and n, but not both 0. Here, m and n. m could be 0, n could be 0, but they cannot be both 0. Yeah. All right. Yeah. If they're both 0, their greatest common divisor does not exist. That's the reason. Does not exist. Okay? So that's what we require. So they cannot be both 0. All right. So then we need to find their greatest common divisor, GCD of m and n. Yeah. Simple question. Computation question. Yeah. But there is some interesting property here. Yeah. So we want to learn from this simple problem. Yeah. All right. Yeah. Middle school procedure. Yeah. Yeah. Let's recall. Yeah. 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 So you know how to calculate. Yeah. So here, recall middle school procedure. Step 1, find the prime factorization of n. Yeah. You can do prime factorization, right? Yeah. Step 2, find the prime factorization of n. Yeah. Step 3, find all the common prime factors. Yeah. Common prime factors. Right? Step 4, compute the product of all the common prime factors. Yeah. Including power of the prime factor. Yeah. Power. Yeah. Prime. Prime to certain power. Yeah. All right. But so this middle school method relies on prime factorization. You need to do prime factorization, right? Yeah. You need to do. Yeah. Here, let me use a simple example to show you these 4 steps. Yeah. To calculate GCD of 60 and 24. Yeah. First, let's do prime factorization. 60 equals 2 squared times 3 times 5. Okay. So here we use 3 primes. Prime 2 is first prime. 3 and 5. You know prime, right? Yeah. So you know the meaning of prime numbers. Yeah. All right. 24 prime factorization, 3 cubed times 3. Then let's calculate the common prime factor. Yeah. So for power of 2, the common part 2 squared. Okay. For prime 3, the common part 3. Prime 5, no common part. Okay? Yeah. So at the end, we multiply their common prime factors. 2 squared times 3 equals 12. Okay? Yeah? So that's the middle school way. All right? Yeah. Middle school way. Okay? All right. Yeah. So, but here, if people are satisfied with this middle school method, then we do not need to do anything, right? Yeah, we can start if we are satisfied. Yeah, yeah. Well, but we're not satisfied. This middle school way has some big problem. Yeah. So what's the big problem? Yeah. Yeah. So when you come back, come back after midterm. Okay. Next week, that's our midterm week, right? Yeah. The first class Tuesday, I do review. All right. So I do not cover new materials. Yeah. So let's delay it after midterm. So on Tuesday, I do review, explain questions from your quizzes and your homework assignment. Okay? Do review session. Then Thursday, so you come to the classroom, we do part B, 10 computation questions of midterm. Part B. Okay? That's next week. Yeah. All right? Yeah. So the new deadline tomorrow. All right? Friday, tomorrow. Yeah. New deadline. Homework assignment number 1. I changed. I give you 2-day extension. Yeah. Yeah. So try to do the best you can. Okay?